Welcome to TNG's Big Tech Day 25. Today we're investigating to what extent humanoids can use a world that's made for humans. I am Daniel, consultant at TNG. In the past, I have developed autonomous driving, I've automated the work that lawyers do, and now I'm thinking about or researching how to make robots intelligent. And it's my pleasure to welcome Thomas Endres, partner, managing director, and co-founder of the Innovation Hacking Group that's responsible for the showcases you'll see today. It's also my pleasure to welcome Tobias Lübbe. He's a master's student at the Technical University of Munich. He has a background as a mechatronics engineer, and he's writing his thesis at TNG on robot foundation models. So it's been inspiring to see what robots can do, specifically humanoids, in the last 6 months. They've developed very quickly. And when Henrik Laggers and my client, Patrick Lanners, met for lunch, they were speaking about this and asked themselves, to what extent can these robots use a world that's actually made for humans? And because Patrick works at BMW and we have a humanoid robot, we decided to teach it to drive. And this was for an exhibition at BMW's Innovation Summit. We'll use this as an example of, or to explain to what extent these robots can use a world that's made for humans.
Okay, so to make this happen, when working with such highly integrated systems, it was clear that we will be facing problems on the mechanical side of things, as well as on the electrical side of things, and also software-related problems. And probably many of you have heard the slogan of TNG, that we solve hard IT problems. And as all of my amazing colleagues here are showcasing today, we really do. But at least I have never heard the slogan, we're TNG and we fix your mechanics. So we had to move quite a bit out of our comfort zone to make this happen. So let's see how we did. Looking at the mechanical side of things, it's important when driving a kart to find a stable seating position to compensate for external forces while still maintaining the intended steering angle. And for a human, this is quite intuitive to do because we subconsciously do a little micro adjustments of our seating pose. But for a robot, this is a new task and not too easy. And first thing that comes to mind when trying to seat this robot in the kart is that it's substantially smaller than an average human being. And indeed, when we placed the robot in the kart, it was sliding a lot around, like within the factory setting of the kart that fits most humans. But luckily, there's a solution for that exact problem, because children are facing the same issue once they are karting. And by using not one, but two of those foam seat inlays for our go-kart, we found a good fit for our robot. And the solution has the additional benefit of bringing the robot a little bit higher and more to the front of the kart, making the pedals and the steering wheel better accessible. However, the pedals still were not reachable for the robot. And again, we can repurpose a solution built for children and just use those pedal extensions that finally basically provided a perfect fit for our robot. So now the robot has a nice seat and is able to reach the pedals. But what about the most central human interface in a go-kart? What about the steering wheel? So most steering wheels are built for human hands. And human hands are incredibly dexterous with 25 degrees of freedom and provide excellent gripping strength. And looking at the hands of our robot, which is actually not this exact robot, because this is the cheap version. It has just silicone hands without any motors. The robot that we are actually using in the go-kart has more elaborate hands, but it has only 3 fingers, and I think it's about 9 motors, 9 degrees of freedom in one hand. And these hands are obviously lacking dexterity and gripping strength to properly grip the steering wheel and turn it. And to face this issue, we first broke the problem down to just handcuffing, basically, the robot to the steering wheel. So it's kind of doomed to drive. And this prototype was quickly built with a little woodworking and 3D printing. And this concept of just handcuffing the robot to the steering wheel worked so well that we kept it for the final solution, in which we just redesigned our 3D prints a little bit, but the concept stayed the same. And this solution also has the advantage of further fixing the robot in its driving position, making all the downstream tasks way more easy to solve. All right, so that solves the mechanics. Let's look at the electrical adaptations that we had to make to our go-kart. With the original steering wheel, one can simply press and hold a button to drive backwards. And backwards is sometimes very needed for the go-kart because the driving radius is quite big. And being handcuffed to the steering wheel, this wasn't an option for the robot anymore. And therefore, we had to mimic the button press in the low voltage system of the go-kart somehow. And this is not too hard to do. We just used an electric relay controlled by an Arduino, and that worked like a charm, out of the box, no problem at all, easy peasy. But once we placed the robot in the cart and turned it on, the Arduino was behaving completely random. And we slipped into one of those feared debugging hells, didn't know what was going on, started questioning ourselves. But finally, we noticed that when shielding the Arduino with our bare hands, the Arduino was behaving deterministically again. So how can that be? We finally came to the conclusion that the robot is producing such electromagnetic smog and radiation that this affected the electronics of the Arduino heavily. And now that we identified the problem, the solution was also quickly found. We just covered the insides of the housing of the Arduino within the steering wheel with aluminum foil, and that worked like a charm. So now that the electrical and the mechanical problems are out of our way, we can finally move on to our home ground and solve the hard IT problems. The first problem was that we couldn't move the joints, so we had to learn how to program the robot, and Unitree is providing an excellent SDK for controlling individual joints, and we can just send a target value to one joint. And this directly solves the problem of accelerating and braking, because we only need one joint for that, right? So let me replay the video. This is one of the examples when we first learned how to control a joint. We don't need more than just the ankle joint to press the pedals, and that's the solution that we are still using. So maybe
finding it.
Ah, cool. Thanks, Thomas.
Solve hard IT problems.
Exactly. Yeah, so this is basically braking and accelerating at the same time. Of course, we do this differently now. Yeah, but steering is a little bit more complicated, because to steer the steering wheel, the hands have to perform a 3D arch trajectory while still maintaining the same distance between two hands. And to make things even more complicated, the pose of one hand is defined by the kinematic chain of one arm, which has 7 degrees of freedom compared to the 60 configuration space of one hand. This means that there are infinite solutions for each pose of the hand. And of course, there are numerical solvers that can produce nice and continuous trajectories for each individual joint. But we found an even simpler and, we argue, better solution for that. Because since we are handcuffing the robot to the steering wheel, the trajectory doesn't need to be perfectly accurate. And we found out that just recording 5 intermediate steering poses, so from all the way to the left to all the way to the right, enables us to linearly interpolate between those 5 poses on joint level, and that was just good enough. And this also has the benefit that we can quickly adapt to new robotic embodiments. We just have to place the robot in the cart and record the 5 new poses. And this further enables us to engage the whole body in the steering motion. Because if we record the poses once the robot is sitting in the cart, we can also record all the joints, for example, the hip joint and even the leg joints, to support the steering motion. And this provides the robot with the necessary core strength to steer the cart. And here you can see the robot booting and getting in its driving position, and you can see as it's lifting its legs, there's a lot of core strength now, and there you can see the steering trajectory being performed. It's a little jerky, but if the robot is handcuffed to the cart, that's enough.
And it looks absolutely hilarious if you
It
have
does.
a robot looking like that
Yeah, absolutely.
on a crane.
Exactly. So now all components of driving the cart are solved and integrated in one system. And it's important to note that all those components are related across domains with each other. So changing something in one domain can have very well side effects on any of the other domains. And we experienced that with our Arduino because the mechanical decision of placing the Arduino close to the robot had massive effects on the electrical domain. And therefore, integration can be tricky sometimes with such systems and needs to be tested thoroughly. However, now everything works brilliantly, and it's a lot of fun, and we can't wait to show you. So here's our first proof of concept, in which we just did a key mapping to an Xbox controller and drove the cart like an RC cart, and it's just amazing to see the robot drive the cart.
All right. So now that we've controlled the cart, we should also think about letting it drive autonomously. And therefore, we need a lot of different hardware. We need a lot of things to actually see the environment. And this is where the sensors of the robot come in. And here you can see basically the most important sensors. So if we have a look at the face, there's an RGB camera. Up here, there's also a few more cameras. Here's a LiDAR sensor, and all of those can be used to really control the car. So basically, the RGB camera will basically work like a webcam, so you will have a picture like that. For the 3D perception, you will basically get the same picture as you have with the RGB camera, but with different colors actually, and the colors now reflect the depth that the pixel is away from the viewer, so that the pixel is away from the camera actually. And this blue area here is pretty close to the viewer, and here we have something that is still close but not as close as the steering wheel here, and then the further away the object is, the redder the image gets. So this is basically like a heat map. If we want to do even more things with 3D maps of the world that we get, we will probably use the LiDAR, which is this thing down here. It is a 3D perception. It offers us a 3D perception of the world. So what we get is normally a point cloud, and with this point cloud, for every point that we get, we have a direction that the laser that this LiDAR is based on is currently turning, so it's turning around all the time and giving us feedback of the real world that we have, and at the same time it also gives us the angle. So, and with that and the depth, we can then construct something like this here. And here you can see sparse points up here. So here the objects are farther away, so the points are a little bit sparser. And if we have something that is close, then the objects will be closer, so we will have a denser point cloud here. And what you can see here is, who knows this building by heart? Can anybody guess where that is? It's hard to tell. It's actually a museum. So this is the Deutsches Museum in Munich, and this is the robotics department. Maybe you have seen some of the robots here in the point cloud. And you can also see some humans walk around here. And if you have this image now, you could reconstruct a 3D representation of the world around you with multiple sightings that might be possible using techniques like simultaneous localization and mapping, or in short, SLAM. And you can also combine that with other sensors to get an even more precise view of the world. But we didn't need that actually for our first use case, which was somehow semi-autonomous driving, and this is what we did here. So here you can see basically the RGB image from the camera, and what we tried to do now is we tried to implement some basic line following algorithm. So the idea was that we put some tape on the ground, orange tape actually. This is blue because the colors were inverted. We didn't fix that. But nevertheless, you can see that clearly, and it differentiates from the rest of the ground. Unfortunately, it does not really always differentiate from the steering wheel, which somehow looks a similar color. So if we just do a line detection on all of the image that we get, we will probably also get some lines here. So what we needed to do is to filter out everything that belongs to the card. And there the depth perception comes in, because we can just filter out everything that is pretty close to the camera. And with that, we can then just mask that out and just use the part that is relevant for us, do some line detection here, and we can then use some standard algorithm, half lines here, that you can see here in the picture. Yeah, don't panic. With that, we can then move the card relative to the line position that we have. Unfortunately, there's still a problem here, because, as Tobias said before, when the robot steers in this direction, it also moves its hip into this direction. So the camera, unlike with other cameras that we have on cars, is not always perfectly aligned with the center of the car. So we also need to find out where the center of the car is located. And that's where this beautiful part comes in. So this is an Aruco tag. It looks like a QR code a little bit. It's also similar. And we can just detect that using open computer vision libraries like OpenCV. And with that, we now have the center of the card as a center of the Aruco tag, and the center of the line where we need to go. And with that, we can then define in which direction the card will be steering. All right, so what else do we need to make a robot do all these things? And there are three main parts which contributed to the revolution in robotics, which only made this little robot possible. So the first thing we need is the battery. So if you turn around, okay, you can see underneath the elbow, there's the battery. And the battery is pretty small for such a huge amount of power that it hosts. And this has changed in the last few years. The battery density has gone up significantly. So we need less volume, we need less weight for the batteries of the same capacity. And this is one of the key drivers why we can even do this today. And at the same time, of course, the price has also gone down, and this enables even us as TNG to own such a robot. And the second contributing factor is motor strength. So here we can see a motor from the inside. This is actually one of the wrist motors that we opened because we needed to open it. Actually, we will get to that in a minute. You can see that it looks pretty advanced, and it is pretty advanced. So the advances in motor technology have been significant within these last few years, and this is very necessary. Because if you have a look at this arm, that's first we have the shoulder motors here. Then we go down to the elbow motors. Then there would be some wrist motors for the more advanced one. Then we have some motors for the fingers, and so on and so on. And all of this weight has to be lifted by the shoulder motor, while at the same time it also has to provide some extra lift to be able to carry out its task itself. And this kinematic chain that we have with these advanced robots is pretty hefty, and with that we also need very strong motors. And with the upcoming of neodyme magnets in these motors and some other advances that we had, we've gone a long way from motors that we had in the 2000s to what we have today. And this is, of course, also due to the advances that we had within the car industry, because there we also, this is somehow the driver of all this revolution in the electric motor. All right. The last thing, and this is pretty obvious to us, but nevertheless it's very important, is that we also need some compute power within this robot. So you cannot just have a microcontroller in there, but in order to have some serious AI going on within the robot, you also need the compute power in it. And nowadays it is possible to have very advanced chip card-sized computers that also offer us the possibility to process some neural networks inside and have some pretty interesting VRAM specs and so on and so on. And this is, of course, an ongoing thing. This has been going on like since the 60s or something like that. But nevertheless, it is also possible to be completely autonomous for the robot this way. And then, if we want to talk to robots, so the use case I want the most is a robot that brings me coffee, so I also have to tell it to bring me coffee. So the idea behind that is, of course, that it also can hear me and can talk back to me as well. And for that, we don't only need the neural networks, so speech-to-text or text-to-speech neural networks, but we also need microphones and speakerphones in the robot itself, and this is also what it offers. All right, so now that we know what we need, now that we have some software to do that, and we can also drive the cart, what did we actually do with it? So one thing is, we went to the Deutsches Museum with it. And here you can see some pictures from that event. So we tried to put a smile on a few kids' faces and make them think about robotics a little bit more. And you can see that we walked around with the robot. We also drove around with the robot. Actually, we blurred the license plate. I'm not sure why we needed to blur that, but nevertheless, okay. And one thing why I think we blurred it, we also put some children on top of the cart and let them drive with us, but that's a different story. Nowadays, it's not even necessary to put them on the sides of the robot, but we can also have a trolley in the back, so you can relax and enjoy your trip with the robot who is driving itself. And then, nowadays we are also trying new things out. So we're putting the robot on a bike and letting it drive the bike. Unfortunately, so this is work that is currently ongoing, so it's not finished yet, but it also broke the bike already once. So, and with that, I'll give it to Daniel.
Right, so the advances are amazing. We have these humanoid robots that are consumer products that can do, I mean, this video is buffering, but the robot is really smooth. That can do, they can do these sort of amazing looking movements. But I want to go back to the original question, which is, to what extent can they be helpful in the real world and use the world that's made for humans? And I'll consider an example. I'm asking, would you have this robot bring you coffee or do work with you inside your home? So the most important thing for having a robot at home is that it's safe. Right. So bugs happen. At the moment, these humanoids are fairly they're fairly complicated, and enthusiasts are programming them, but they're not particularly safe. Bugs happen. But even worse than that is, if they're controlled by a human, it's fairly hard to program them so they're precise, and for humans to control them precisely. So here we were filming a race between a go-kart and a car. But the floor was slippery, and I misjudged how much I should turn into Henrik, and he had to jump out of the way. But I'm glad to say we haven't had any accidents, and we only sort of operate at 30, 40 kilometers an hour when everyone's paying attention. So safety is important, but even if humans are controlling the robot, it can be unsafe. The next point is stability. So these boxing matches are again super interesting, but I actually point to a very important thing, which is you have humanoids on 2 legs, which means you always need power in order to be stable. If you have this at home and a dog, for example, runs into it, you have the risk of it falling over and really damaging your property, which obviously isn't desirable. And there are several ideas of how to cope with this. One of the points is you can reduce the center of gravity by using the hands also as legs. This is a video from yesterday. It's exactly the same robot, but
creepy at all.
but it's been made safe for home use, sort of. More generally speaking, you can lower the gravity, but actually, if you've got flat surfaces at home and no obstacles, you can replace all of the legs with just a wheeled system, which is very stable, and then you maybe have the intelligence of the arms and the camera to do the work that you wanted to do. But at least it's a step in the right direction of making these humanoids safer. Here I was doing a gym session with our robot. We were doing lifts. So before we bought the G1, I wanted to measure how much torque the elbow joints could produce, so that we could make sure that there was enough torque to steer the steering wheel. I filled up a bag with bottles of water and sort of measured, can all of the joints still work? And we realized it has just about enough torque to turn the steering wheel of an adult go-kart, but it wouldn't have enough strength to, for example, lift a 5 or 10 kilogram rucksack that you have at home. So you're fairly limited. Even though the motors have gotten a lot better, they're not perfect yet. And this is an active decision by Unitree. The G1 is sort of light and nimble. You can put in stronger motors, but then again, you have more weight and more risk of sort of serious injury. I said the motors are just about strong enough to steer a steering wheel, but they get damaged quite easily, the elbow joints, because you do have, you're sort of operating at limits. So in fact, just before one of our presentations, the robot broke, and we had to replace the motors. Here the thing is, these Unitree robots, they're fairly new, which means getting the components you need to replace it is fairly difficult. The delivery times can be several weeks, and it costs several thousand motors. But replacing it is actually fairly easy. You can just unscrew the forearm in this case. You have to cut some wires, and then you solder on the replacement part.
One thing that we need to prepare as well, so the robot now needs to go to sit in the cart, and so he'll be available in a few minutes for you to drive around with it, but he needs to leave now. He needs to prepare a little bit.
Okay.
See ya. Oh God,
Yeah.
that's not gonna be a good driving experience. I think he needs to do a test first.
Reicht dir die? Das Interview auch.
So this is obviously loads of fun. We've really enjoyed doing this project. A lot of it was done sort of in the evenings and at night. But I think you got an impression for how humanoids have changed. They're now consumer products that you can just buy. The cost is reduced by about a factor of 10 in the last 3 years. And just one point before I finish, I was asking the question, to what extent can I use the world made for humans? And one of the things that isn't working yet is the dexterity. So we had to sort of lock it into the steering wheel. And that allows us to do this drifting, here in Motor World. But these precision tasks where you need dexterity, they don't work yet. One of the things we tried was to teach you to put on a hat. And in order to do this, you need to understand the geometry of the hats. You have to understand where exactly to grip and how precisely to grip. And that's actually a much harder problem than teaching it to drive. So yeah, summary is consumer products, that's absolutely amazing. You can get one, it's just 20,000 euros. We've had a lot of fun doing this. And one thing I realized was, TNG is known for software, it's known for AI, it's known for cloud, but not so much for the mechatronics stuff. But actually, we have loads of PhD students, or people who did their PhD in robotics, and it's been quite easy to debug, because all it involves is, asking one of these people, what do I do? And they tell you exactly what to do. Maybe you'll see loads of great sort of videos in a moment with robots doing things. And I should point out, a lot of the time it's not autonomous. So usually you have a human doing it, and the reason is they're not intelligent yet. So they're not yet suitable for the human world because they're not smart. If you have any questions, feel free to get in touch. And you can join us after this talk to drive the go-kart with the robot in yourself.
Yeah. So we have now time for a few questions. Then we'll have the experience with the robot. We reserved some extra minutes just for that, so that you can also see it in action. But first, maybe let's take some questions.
Yeah, thanks a lot. I got a bit attached to the little guy here. If there are any questions, please raise your hand, and I can hand you the mic.
First of all, thank you for this talk. And my question is, so to these spontaneous movements that we observed during your talk, were they pre-programmed to keep our attention, or it's like the wishes of the robot to do it?
I'm not sure it's the wishes. So in order to keep stable, sometimes you have to make micro adjustments. So I think it's something like the wind's moving, and so it's just adjusting its feet. But the science it was doing with the hands was the operator sort of making jokes.
Can you use these robotic foundation models to control these robots?
Mm-hmm. Yes, that's the plan actually. So we want to control the robot with robotic foundational models. So and this is also what our next talk is about at 4:15 today. And there we will talk about how to apply that to not only those robots but also other robots. And the idea, or the main idea that we had when buying this robot was to really use the robotic foundational models to make me coffee.
Yeah, and we actually already tried deploying a foundational model to our G1, and it kind of worked, but not well. And again, robot foundation models are very much about data, and it's hard to collect data for this robot because there are no great remote control options, fine-grained remote control options yet, and also the simulation frameworks that we have are not yet that advanced that you can produce good training data for it. So this is the main issue that we're facing.
All right. With that, we leave you with one last thing. There was a short scene from this movie already in our talk, and we recorded a robot racing a hypercar, so the Porsche GT RS3, and we made a little video about that, and that was a lot of fun. Let's have a look. Okay, I think the robot had enough time to prepare now, and we can actually see him live in action at the Motor World. So at the entrance, we set him up. And so if you walk with us to the Motor World, we can then have a look at it.